Mohammed. I'm a second-year master's student at Harvard Medical School, and this is our first episode of the HMI speaker series. So HMI stands for the Harvard Medical AI Club, which is a student-run club at Harvard Medical School that we just started. And this is a speaker series where we will introduce researchers to talk about their um, recent, interesting medical AI research. So this is the first episode, and in the first episode with us is Roman Hardy. Roman is a second-year AIM PhD student at Harvard Medical School. He did his master's at UC Berkeley in information and data science, and he did his bachelor's in math and astrophysics, also at UC Berkeley. Roman is also a Janssen fellow at the Department of Biomedical Informatics. So he'll talk to us about his research in reconstruction, AI-based reconstruction of colonoscopy. So, Roman, take it away.
Yeah, thank you. Let me see.
Sorry, so before we start, this meeting is being recorded and it's going to be uploaded to our YouTube channel, which I'll share the link for here. So if you don't want your face being shown for any reason on that channel, you can not share your face. Otherwise, enjoy.
Yeah. All right. Are you ready for me to start?
Yep, you can go.
Okay. Yeah, hi everyone. So as Mohammed mentioned, I'm a second-year PhD student here at Harvard Medical School in the Roche-Picard lab. And over the past a little bit less than a year, so I just started at beginning of 2025, I've been working on 3D reconstruction for colonoscopy. This is my first research talk, actually, officially. So hopefully this goes well and everybody gets something out of it. I think there will be a time for Q&A at the end, but if you guys have any questions during the presentation, you can put stuff in chat and I'll do my best to answer dynamically. Can everyone see the screen all right? Is it showing up?
Yep.
Okay, perfect. Okay, so yeah, this is a brief outline of what I'll cover. I'll start by motivating the research problem a little bit, why we care about 3D reconstruction for colonoscopy in the first place. Then I'll move on to more of the technical aspects. And I've tried to include a mix here of like true technical detail, but also some intuition for people that aren't as interested in some of the math and the machine learning. Yeah, 3D reconstruction, I think, is a really active area of research right now, and a really interesting one to approach from an endoscopy setting. And I'll spend most of my time, I think, talking about the paper that I recently got accepted, which is ColonCrafter, a depth estimation model for colonoscopy, and some of the things that we did for that project. And then finally, I'll have a few slides at the end talking about future directions and where the lab and my research is heading specifically. All right, so, oh, by the way, a little word of warning, there's going to be a lot of images of colons, unsurprisingly, given that my work revolves around colonoscopy. Hopefully not too upsetting, but yeah, just thought I would mention it in case anyone is squeamish and doesn't really want to look at these. Maybe you can keep me on in the background. Yeah, so I thought I would start with a couple of slides talking about why we care about 3D reconstruction in this space in the first place. And really what it boils down to is that 3D information is kind of crucially missing in GI endoscopy. So what you're seeing on this slide here is just a visual representation of what actually happens during a colonoscopy. And I assume most of you probably haven't had this procedure, but you probably will at some point in your life, just because it's considered the gold standard for colorectal cancer screening. So it's really a very important medical procedure, but also a very uncomfortable one. And I've shadowed my fair share of colonoscopies at this point at different hospitals, and yeah, it's not a pleasant thing. The reason I wanted to show this is not only to introduce you to what colonoscopies are, which is, this is a procedure where you feed an endoscope through the rectum of the patient into the colon, typically to look for and resect polyps and prevent colorectal cancer that way. But also to highlight the fact that the only information visually that's available to endoscopists during this procedure is 2D. So there's a little camera and a light attached to the endoscope, and that plays or that relays into a live video feed that you can see the endoscopist in light blue is looking at. Um, but this feed is 2D. So the endoscopist is navigating this very complex 3D anatomy, even 4D, and sometimes we treat it as 4D because it's highly deformable and moves through time. Um, but they're doing it using only 2D visual information, and in some cases that's insufficient. So um, what's happening internally inside the mind of the endoscopist is they're really forming their own internal 3D model of the anatomy, but sometimes these mental models fail, and we want actually more precise visualizations of what the anatomy looks like from a 3D perspective. And this lack of 3D information is really even more apparent when you look at clinical reports covering colonoscopies. A colonoscopy will typically last around 15 minutes. And so if you're capturing a video during that procedure at 30 frames per second, you're getting just shy of 30,000 images. But what actually ends up in the colonoscopy reports themselves is only just a handful of thumbnails. So the endoscopist will pick some kind of key frames from the colonoscopy videos, which highlight things like polyps, artifacts, lesions, essentially, with associated text. And these are high quality summaries for the most part. They do summarize pretty well what's happened during the procedure. But when it comes to tasks requiring spatial information, so things like lesion locations, lesion sizes, it's highly insufficient. You can't get very reliable estimates of the way that polyps look, what their sizes are, where they're located, just from these 2D images and from very imprecise text locations. And so the way that this affects, I guess, this leads into, I guess, adverse clinical outcomes. And I thought I would highlight a few. These are slides that I've borrowed from Dr. Tyler Berzin, who's a close collaborator at the Beth Israel Medical Center, where I do a lot of my shadowing. So I thought I would highlight three here, which I think highlight the problem pretty well. The first is that polyps actually go missing quite often during colonoscopies. So it's not uncommon for a polyp to be seen, especially early on in a colonoscopy, and then kind of lost out of sight behind a fold in the colon. As I mentioned, right, the colon is this highly deformable structure. Polyps can easily be hidden behind folds, and if this mental model of the colon that the endoscopist forms during the procedure, it's inaccurate in some ways and imprecise. It's kind of an approximation um, that they form. And so, when they try to go back to a location where they think they've seen a polyp, they might just not see it, right? They might be at the wrong location. It might be hidden behind a fold, and so they might just miss it entirely. And obviously, this leads to worse outcomes for the patient because now the patient is at higher risk of developing colorectal cancer, and the physicians themselves are under higher stress because they might think that they've caused the patient to have, I guess, more higher probabilities of developing cancer in the future. So in this case, right, having precise 3D information of the polyp and where you've seen it as you do the procedure would be extremely beneficial because then you could kind of backtrack to the place that you've seen it, mark it, resect it, and then just be done with it. A second use case, and the slide shows a stomach, but this is also applicable to colonoscopy as well, has to do with inter-physician communication. So when a large lesion is seen, so think a polyp, oftentimes what happens is the patient will be referred to a specialized center for resection or surgery. So the person doing the initial procedure, what they have to do is send some images, like you saw in the colonoscopy report, some 2D images with associated text describing the lesion and its location. And then the surgery team that has to do the resection, or the endoscopist doing the resection, uh, in the second location has to infer from that exactly where the lesion is, what it looks like, and this is kind of a non-trivial task, and it leads to a lot of headaches. And surgery, right, is a non-trivial procedure. And so if you know go to the wrong place and try to resect something that isn't an actual lesion, you could harm the patient. You could cause them, you know, basically undue health burdens if you're inaccurate in your estimates and kind of imprecise in your surgery planning. So here too, 3D information would definitely be invaluable. And then finally, I thought I would highlight this use case, which I find quite interesting, which is also related to follow-up procedure, but this is more for disease monitoring and monitoring kind of the status of patients after procedures. So this is a case where um, after resection, a patient comes back for a follow-up surveillance colonoscopy to see if the lesion and the scar from the resection has healed properly. So this image that you're seeing, there used to be a polyp there, but it's been resected and now it's scarred and it's healed. But I think to the naked eye, unless you're like a highly trained endoscopist, really you don't see much, right? Maybe the tissue is a little bit less vascular than surrounding tissue. It appears a little bit paler. But you know, as I mentioned, you know, the colon is highly deformable. So if you got a slightly more occluded view, or you know, a slightly noisier view, you might not even notice that this was the former site of a polyp. And so the person doing the follow-up would then have a much harder time tracking the disease status, whether the patient is properly healing, and you know, contrast that to a system where you had a way of marking on a 3D model where the polyp was, and of tracking exactly where you were in the colon. The person doing the follow-up would immediately know where they were and if they were in the site where the polyp was removed, and then they could do this follow-up much more easily. So hopefully this motivates why 3D information is important in colonoscopy, and the fact that it's missing kind of motivates computational approaches to provide this information to physicians in the first place. The I think now I'll talk more about the actual task of 3D reconstruction, which formally we define as, you know, the task of reconstructing 3D anatomy from unconstrained RGB videos. So what we're starting with is the same videos that the endoscopist sees. So if you recall that first diagram that I showed, that video feed is what we have as input, and then we want to get to a point where we can reconstruct plausible anatomy like this sort of idealized colon model that you see here. And this is a really difficult problem because it's ill-posed, right? There's not a lot of constraints, and one video can actually correspond to a lot of different reconstructions. Of course, we can constrain this because we know what colon anatomy roughly looks like, but even so, the problem is very difficult. And it's made even more difficult by the fact that traditional approaches to reconstruction, since 3D reconstruction is kind of an open area of research, even for open world videos, they tend to fail when applied to the endoscopy domain. And the reasons for this are kind of, you know, there's a lot of reasons. Isolated three here, which I think are very commonplace, which is that there's a lack of distinctive features for tracking. There's very difficult lighting conditions, and the tissue is constantly deforming. So, you know, even more so than in open world videos, I think the topology of the colon and the nature of it makes for a very difficult reconstruction problem. And to highlight this, I wanted to play this video of a colon. This is actually not a real colon. This is from a silicone model from a data set called C3VD that's been released this year. But I think it does a nice job of highlighting some of the difficulties that you face with colon videos. So you can see on the left side, there's kind of this very intense bright spot because the light source, which is co-located with the camera, is up against the mucosa of the colon. And so it's reflecting a lot of light back into the camera. The tissue is constantly deforming. There's debris. There's specularities, which show up at these like bright little speckles. which also then confuse reconstruction efforts. So even with this kind of silicone model, which is idealized, and it even has like a simpler camera trajectories than what you see in actual clinical videos, you start to see some of the challenges that 3D reconstruction efforts face. Okay, so given that the task is so difficult, how do we approach it? So in typical machine learning fashion, the paradigm is to break it up into smaller tasks and then deal with each one independently and then try to have them come together in a cohesive manner at the end. So the task that I guess I focused on uh, at the start was depth estimation. And really, I think this is probably the most integral part of 3D reconstruction because with depth estimation, what you're trying to do is estimate the third dimension from 2D videos and 2D images. So to make that a little bit more formal, what we're trying to do, or what we try to do with at the start is this task called monocular depth estimation, which tries to predict relative depth for every pixel in an image and every image in a video. And it's called monocular because the images in this case are assumed to be captured with a single camera, which is the case with colonoscopy. Now, again, this is actually an ill-constrained problem, um, but in this case, light and geometry gives you very powerful cues about depths. And you can see that in this open world video of a flower. The flower in the foreground has very sharp edges. It's not blurry like the background, and so this has led people to apply deep learning to depth estimation, and you can actually get pretty good performance on these images, being able to estimate relative depth pretty accurately. But again, there's problems when you move to colonoscopy for the same reasons that I mentioned earlier. Um, the endoscopic setting is obviously very different from the open world setting, and images that you see of a colon are very different from those that you see in open world. You won't see any flowers in a colon, and certainly not any bees. Um, so models that are trained on open world videos generally tend to fail on colonoscopy. Um, in addition to that, there's a lack of training data. So if you want to train a depth estimator specifically for colonoscopy, there isn't a lot of ground truth annotations available. There's no depth sensors attached to endoscopes, so you can't use something like LiDAR, which is used for like self-driving cars. You can't really have physician experts annotated because you don't have like measurements. They can't really go inside the colon and take out a ruler and measure how far the camera is from the colon wall. It's just completely unfeasible as well. So you have to either train with synthetic data, which I'll talk more about, or train them in self-supervised ways. As I mentioned, there's difficult lighting conditions. And then another aspect which we're trying to address with Colin Crafter, which is the paper that I'll be talking about, is this idea of temporal consistency. This is one I haven't touched on yet, but a lot of depth estimation models assume that all of the context is provided in a single frame. So they take one RGB frame at a time, and they try to estimate relative depth from it. And this is fine for some applications, but if your goal is 3D reconstruction, the reason that it poses problems is you get temporal inconsistencies across time from different depth estimates of the same scene. So to give you some intuition for what I mean here, you can imagine two successive frames from a colonoscopy looking at a polyp. So in the first frame, maybe a pixel corresponding to the polyp, you estimate its depth to be, let's say, 10 millimeters away. In the second frame, let's say your camera moves forward like 2 millimeters. For a pixel corresponding to the same polyp, you would now expect it to be 8 millimeters away. The problem is if you have a depth estimator that predicts only on single frames, you might miss out on that temporal context. So you might predict maybe 10 millimeters away from the polyp in both frames, even though the camera is now moved forward. And so what you end up with, even if the relative depths are relatively accurate for each individual frame, when you try to reconstruct the surface by combining the depths from these two frames, you get a lot of noise. And you want a clean surface geometry, which you don't get if you don't model across time as well. So hopefully that makes sense. With Colon Crafter, we've tried to address these issues by making a model which doesn't predict on just single frames, it predicts on videos. And it's able to learn robust geometric priors from synthetic data. And then finally, it uses a dynamic style transfer approach to adapt images to its own synthetic training domain, overcoming the domain gap that typically plagues models that are trained on synthetic data. So this is what I'll be going over for most of the remaining slides. First, just a quick primer on diffusion models. I don't think there's enough time to do a very in-depth dive into all of the math behind diffusion models, but since it's a pretty integral part of the model architecture, I did want to give some intuition again. Essentially, a diffusion model is a generative model that learns to predict clean data from noisy inputs. So during training, what happens is you will take a data sample from your data set and add Gaussian noise to it until it's basically destroyed. And then you will task your diffusion model with predicting what the clean version of the data looked like, but all that it uses as input is the noisy version. And if you do this at scale on thousands and thousands, millions of images, the diffusion model ends up learning extremely strong priors for what the distribution of your data actually looks like, so much so that it can generate completely synthetic samples that look as if they could have been realistically drawn from the data distribution. So there's this kind of nice example that I included in the bottom left here with a dog. So the diffusion process, this act of adding noise and destroying the input image, is shown on the top, where you start from this clean image of a dog, and then you progressively add Gaussian noise over several time steps until it's basically all noise. And then what the model tries to do is this reverse path in the bottom, where it goes from this Gaussian noise back to the image of the dog. And then at inference, it starts from pure noise and tries to, or it does outputs, high resolution, high fidelity images that look as if they've been drawn from the true data distribution. Another aspect of diffusion models, which is important for what we'll be covering later, is this idea of conditioning. It's not necessarily specific to diffusion models, but it's very common nowadays. If you've ever played with something like DALL-E or Midjourney, or I know Sora has been getting a lot of attention in the media recently. These are examples of conditional diffusion models. So you give the model a condition, usually text, about what you want the output to look like. And this serves as essentially a hint that guides the diffusion process towards something that you desire. So, if you want, I don't know, say you were to go to Midjourney right now and say, I want an image of a dog like dancing with a hula hoop, that text would be encoded. It would be combined into the denoiser in some way, usually through cross attention or concatenation layers. And this serves as a guide for the denoising step. So then hopefully, assuming you haven't, given it something that's like too out there, it'll generate an image that corresponds to the condition that you feed it. So Colon Crafter itself, this is what it looks like. I don't want to claim complete authorship for this architecture, since it was largely borrowed from another work called Depth Crafter, which is the inspiration for the Colon Crafter name. But it is also a conditional diffusion model. So I'll step through it one step at a time to show you what the inputs are and what it's doing at all points. It is a conditional diffusion model that uses or tries to predict depth maps, which is our ultimate goal in this case, conditioned on input images, which are colonoscopy videos. So the inputs are shown on the left, X being the video that you want to predict the depth for, and D in this case being a ground truth. And I'll talk at a later point in the presentation about how we construct this paired data set. So don't forget about that. The inputs are fed through a variational frozen encoder, which reduces the dimensionality of the data to something that's more tractable and easier to handle. And then what you get from this is a lower dimensional latent representation of the original video and the depth map. So that's denoted Z superscript X and Z superscript D. In the typical diffusion paradigm, your target in this case is depth. So we add noise, and just much like you saw the image of the dog being progressively noised. What we do in this case, the dog is our depth map. So we add noise to it over a certain number of time steps until it's essentially destroyed. And then this noisy version of the depth latence will be concatenated with our condition, which is the image latence, Z superscript X, and fed through a spatiotemporal denoiser, which is just a fancy term for a UNet model, which operates on spatiotemporal data. So it's just indicating that we're dealing with videos instead of images in this case. A fancy name for something that's really not that complicated. And then what the denoiser will output is, or what it tries to output at least, is a clean version of the noisy depth latence. So remember, the denoiser takes in as input the condition, which is the image or the image latence, and then the noisy depth latence, and then it tries to recover what the depth latence looked like before we added noise to them. So yeah, so these are the clean latents, and then if you feed them again through the decoder part of the variational encoder, you get back the full resolution depth volume for your video. And as I mentioned, your training objective is to minimize the difference between your predicted clean latents and the actual clean latents, so Z hat and Z in this case. So fairly simple objective. There's just one loss term. We don't add any very fancy regularization or constraints. So just from this is able to learn very, very strong geometric priors for what depths are actually like plausible for colon anatomy. And I should also mention during inference, what happens is because you don't have ground truth depths to work with, obviously this bottom section won't be present, but the depth latence will be initialized from random noise instead of from a ground truth depth, which is in this case at inference is what you're trying to predict. But the top row, this conditioning remains. So you're conditioning on a video, now starting with random noise for the depths, but the denoiser at this point has learned to decode that or to predict what the depths should actually look like. Okay, hopefully that made some sense, but I'll take some questions at the end if anybody found that confusing and would like more of an explanation. Now, this is all well and good. I mentioned when I first introduced ColonCrafter that creating paired data for training depth estimation models is difficult, and this type of paired data is essentially non-existent in colonoscopy. So kind of begs the question of how we actually constructed a data set to train ColonCrafter in the first place. And the way that we do this is kind of borrows from previous papers that have also done something similar, which is to create large-scale synthetic data. So specifically, we're exploiting CT colonography scans, which we've collected from an open source data set. And these are patients which have had their colons specifically tagged. So the colon here, if you're not an expert on anatomy, that's fine. It appears as kind of these black masses. So this is a slice taken from a CT scan. What we can do from these scans is we can upload them to a platform, like we use 3D Slicer in this case, although there's a variety of platforms available now. And we can segment out the colon from this fluid tagged CT scan, compute the center line. So the colon is roughly kind of a winding tube. So you can compute at every point roughly where the midpoint is of the colon and kind of reconstruct a trajectory that goes throughout the entire colon. And then when you do this, you can place a camera along the central line, or multiple cameras in this case. And from the viewpoint of the camera, render what the inside of the colon looks like. So the images that you get are what I guess the camera sees when it's along the center line. And the reason you want to do this is because you can also uh, measure from these like virtual cameras inside this synthetic mesh that you create how far away the colon wall is. So you get pixel accurate depth maps to go along with your images. We call them virtual fly-throughs, but it gives you a synthetic data set or synthetic paired data set with images and depth maps, which you can use to train your model, which is what we want. Okay, now this raises another problem, which is actually, if I back up a little bit more, these images look nothing like the colon images that you saw at the beginning, right? They're grayscale, there's no specularities. So, if you naively tried to apply colon crafter, which has been trained only on these synthetic images, to now real clinical videos, well, you'd probably run into issues because it's been trained on images that look a very specific way, and it's learned good geometry, as we'll show, from the synthetic data. But the image characteristics look very different, so it might not generalize well to real clinical videos, which look quite different. Um, so to solve this problem, or rather, before I get into that, what this motivates is, or the question that we're now asking is, how can we match the real distribution of colon images, which is what we want to ultimately predict depth for, to the synthetic training distribution that Colon Crafter was trained on while maintaining the geometry and the lighting cues present in the real clinical videos. Okay, so this is kind of a simple diagram of what we want to get to. We have these realistic images and these realistic videos. This is not what Colon Crafter was trained on, but we want to predict on these. We have synthetic images that Colon Crafter was trained on. So can we transfer the style of the synthetic images to the realistic images to produce something that preserves the geometry of the realistic images, but has now the style of the synthetic images, so you don't get this domain distribution shift, which could hurt model performance. Okay, so again, this will be a not so technical overview, hopefully, but if you're interested, I'll would highly recommend that you check out this paper, which offers a lot more details, and also the original manuscript for my paper, which goes into more of the math and what goes on. But what we're doing, which I think is quite neat, is this process called style injection. So previous approaches, again, this idea of training on synthetic data is not necessarily new, and some other people have tried to do it and also try to address the domain gap. But the way they would typically approach it is using adversarial approaches. So they would train a generative adversarial network, for example, or a GAN, to try to cycle between the synthetic and the real domains and convert them that way. But the problem with that is that you require additional data for training, which might not generalize to all use case, and it's can also be quite expensive and raises the additional headache of acquiring more data. But additionally, there's no explicit, in most cases, there's no constraints or yes, explicit toggles that you can turn on to enforce the fact that the geometry of your style transfer approach needs to match the geometry of the realistic images and the videos that you start with. And that's crucially important for depth estimation, because if you destroy the geometry, then you destroy the depth maps, and then your predictions end up being very inaccurate. So what style injection does, and the reason why I think it's so cool, is you get style transfer for free using a pre-trained diffusion model. Keep in mind this is a different diffusion model than Colon Crafter that we don't even fine tune on any colonoscopy data at all. But just by manipulating the self-attention layers of this diffusion models, you can transfer the style of an image to another image while keeping the content intact. So I'll show you what this looks like. Also, I should mention, this is an image taken from the original paper that inspired our approach, where they apply it to artistic style transfer. So the left side is, I guess they call it the content image. So it's the image that you want to keep the content of while applying the style of another image, which is shown in the middle, to that. So the style transferred images are shown on the right. And you can see in both cases, the things like edges, and prominent geometric features are preserved, but the style of the middle image is definitely, also shows. So we're doing something similar here. And as I mentioned, this is kind of a modulation of pre-trained diffusion models. At the risk of confusing everyone, I think I'll again try to give you a pretty high-level overview because I tried doing a run-through and realized that this would probably be very confusing otherwise. Um, but what we, oops, sorry, lost track. Um, Starting on the left, so we start with our realistic image that we want to style transfer, and our synthetic image, which comes from the training distribution. We want to apply this style to the image in the video. These are going to be the latents for these images are going to be inverted. Latent inversion is adding noise to the latents in a deterministic way, such that if you started the reverse diffusion process, or if you apply the diffusion model to the noised versions at that time step and let it run through to completion, you would get back your original image. So for example, in the top row, if I started now at Z1C with the diffusion model, I should get back Z0, so superscript C. So it's not just random noise that's being added. I guess that's what I want to make clear. It's not like in when we train the diffusion models where we just sample random Gaussian noise. In this case, we're adding the specific noise that would get us back our original image. And this is crucially important detail. So I just want to make sure that it's clear. So you do this over multiple time steps, and then ultimately you get this very noisy latent Z, a superscript capital T. You mix these latents together to produce the Z tilde, and then you're going to start the reverse diffusion process, which is going to be in the middle line in red, from this mixed latent. And here is, I guess, the magic of it, which is you're going to substitute queries from I'm going to substitute intermediate outputs from the content image and the style image during this diffusion process. So you're going to substitute specifically the queries that are extracted during this latent inversion step from the content image at the top and the keys and values from the style image at the bottom during this diffusion process, which enforces that the content from the realistic image is kept and the style from the synthetic image is transferred. Okay, so let me pause because I think this is quite a mouthful and probably one of the more challenging aspects of the paper. To summarize, what we're doing here is we're storing intermediate outputs during latent inversion, specifically the queries for the content images or the realistic images. I'm using those interchangeably. And for the synthetic images, we are storing the keys and the values. And then during the reverse diffusion process, when we actually want to generate our style transferred image, we substitute the queries exactly that we stored from the content images and the keys and values from the synthetic images. And what we get in the output, just to reiterate, we start with this mixed latent, do reverse diffusion, doing this query key value substitution, and then we end with a transferred image, which preserves the geometry of the realistic image, but now contains the style of the synthetic image. Okay, hope that was clear. I did my best, but yeah, again, I'm happy to take any questions on that and elaborate more if I need to. These are some more examples. You've already seen the bottom row, although this is a slightly bigger higher resolution version of it. What you get in the output is you take you have your original realistic images, you apply this style transfer pipeline, and what you get is now an image that has the same geometry as your original image, but is has the texture of the synthetic images that Colin Crafter was trained on, and is missing some of the artifacts that might confuse it otherwise because it wasn't trained on images with those artifacts. So things like specularities, um, debris would basically get masked out by this style transfer approach, and you can see evidence of that if you look at the intensity difference between the style transferred images and the original images. So you can see it keeps the geometry, things like edges, ridges, folds are kept, but the specularities are removed, uh, which highlights how effective it is. And again, I think the coolest part about this is that it's training free, so you can apply this dynamically without having to train an extra model. You just leverage these powerful pre-trained diffusion models, which are available in open source for everyone to use, which is very cool. Okay, so now let's actually talk about evaluating the models. Um, Unfortunately, because clinical data doesn't have ground truth depth that we can evaluate against, we sort of have to constrain ourselves to evaluations on silicone phantoms. And I showed an example of that at the beginning, but let me show you an example from the same data set, but this one includes a ground truth depth maps, which is shown on the top right. So that's that blue to yellow gradient. So on the top left, that is the original RGB image that we want to predict depth for. But what the authors have done, because they're working with a silicone model, which they can measure depth for, and register these depth maps to the actual RGB images, we can now evaluate how good our model um, is at estimating depths on these like pseudo realistic colonoscopy trajectories. So we're comparing ourselves, colon crafter, I should say, against both general purpose and endoscopy specific baselines, um, using a variety of pixel-wise metrics. And we're doing, I should also mention an important aspect is we're doing an alignment step across the entire video to kind of reward models like ours, which are temporally consistent, versus doing a frame by frame alignment, which is common in the literature. But because of that issue of temporal consistency that I addressed at the beginning, we want to emphasize that our depth predictions are not only accurate at a pixel level, but also consistent across time. So this kind of motivates using a single scale and shift parameters to align the predictions to the ground truth. Can give more details on that if need be. This is an overview of our results. I think the numbers are less important than the trends, so let me just highlight a few observations for you. The first is that most of the baselines that we evaluate against are pretty poor on these colonoscopy trajectories. Open world models, I think there's no surprise why they perform poorly. It's somewhat interesting that EndoDAC and EndoSFM Learner perform pretty poorly, but if you actually look at the papers and what they were trained on, they're, I think, more suited to laparoscopic scenes, which are like surgery intensive and look quite different from colonoscopy trajectories. By comparison, colon crafter is much better, achieves much better metrics, although it's not perfect either. But for example, delta one, which is a measure of accuracy where higher is better, is nearly 20 points higher than most of the baselines. Endo Omni is our only competitor, but there's a little bit of an asterisk next to that because it was partially trained on C3VD, which is our evaluation data set in this case. And you'll see in the next slide, the Endo Omni isn't as good as our model at preserving fine details. And one last thing I want to point out in this table before I move on is so we've ablated the use of style transfer in this case. So the last row, which shows plus ST, this means with style transfer. So this shows that applying style transfer, so converting realistic images to the style of our synthetic training domain, helps pretty much across the board. Um, it is somewhat interesting that the base colon crafter checkpoint without style transfer already does pretty well. And this is evidence that it's learning very good geometric priors of how a colon actually looks like and what the geometry of a colon is, just from the synthetic training, which is good news for us. But also, I think it just goes to show that these silicone trajectories on phantom data are somewhat idealized. Most likely, if you were to apply this to real clinical data, I think the benefit of style transfer would be more apparent. Okay. Yeah, very quickly, some qualitative comparisons. Realize I'm taking a lot of time, so I do want to get to the Q&A so people can ask questions about this. Yeah, if you look in the third and fourth row, colon crafter predictions are present in the last two columns. You'll see that it is much better at preserving geometry and fine geometric details like edges. Endo-Omni, which does perform pretty well in a metric sense. A lot of the edges are pretty blurry, and a lot of the open world models, sorry, just generally fail and produce like very blurry, anatomically implausible outputs. Okay, now we've trained colon crafter. We've shown that it can produce reasonably accurate depth maps. I want to bring this back now to our original discussion of 3D reconstruction and talk about how this can now be integrated into 3D reconstruction pipelines. Essentially, what you can do now that you have a depth estimator is combine the depth maps and stitch them together piecewise to produce 3D reconstructions of what the colon anatomy looks like. Um, I think there's a fair bit of math in this, which I think I'm just going to skip over just for the sake of time. Um, what we do is we estimate camera trajectories using the predicted depth maps by minimizing something called the reprojection error, which is estimating camera poses that essentially align with the predicted depths. And this is another place where estimating temporally consistent depths is advantageous because if you didn't, or if your estimated depths were temporally inconsistent, by contrast, the camera trajectories that you would estimate would probably be very low quality, and then this kind of breaks down your entire reconstruction pipeline. So yeah, this is what the reproduction error is. I think the math for this is also best left to the paper. If you're interested, recommend that you take a look at this, but this is also common in reconstruction literature. So you'll definitely see this a lot if you look it up and are interested. But I think this is more interesting. This is the output that you get once you actually estimate the camera trajectories and stitch together the depth maps, as I mentioned. You get these relatively nice looking reconstructions of colon segments. Of course, if you're not an endoscopist, this might not mean much to you. But hopefully, at least in the transverse section, for example, in the top middle, that tubular structure of the colon, which is characteristic of the organ, should be apparent. And what's nice from these reconstructions is you can immediately see, notice missing surfaces, which is a part of the colon topology which is not seen during the video. But it's, the depth predictions and the reconstruction makes that explicitly clear. So if you imagine kind of a dynamic workflow where these reconstructions are produced during the procedure or even after, it would give endoscopists and physicians an estimate of how well the surface area of the entire colon was seen, right? Maybe they missed a polyp or a lesion in kind of these blank areas. So it would be an indication that, if this was provided in real time, they could kind of observe that area that they haven't seen. And another useful piece, as I mentioned, I think at the beginning when I was talking about, motivating the problem, this idea of lesion localization. With 3D point clouds, you can mark or make like I guess, what you might call like a virtual tattoo of the point cloud of certain lesions. which I've shown on the bottom right here. There's this protrusion or this polyp, which I've now colored the points belonging to in blue. So if you were an endoscopist, referring a patient for a polyp removal, you might, manually tag the polyp in this point cloud, hand it off to the surgery team, maybe at a specialized surgery center. They would get this point cloud with now the virtual tattoo that they can inspect and refer to for surgery planning. So it's much more informative than the 2D information plus text that they currently get, right? So when it comes time to planning, like how they do the resection, how they do the surgery, they're much better prepared for what they'll actually end up doing. Okay. Yes, I already mentioned a little bit about missing surface estimation. This is um, kind of a quantification of that. We can create these coverage maps by kind of unrolling the 3D anatomy back in 2D, just showing that this plot is just showing that the coverage map that you get using the ground truth depth, since we're evaluating on silicone phantoms again, is very similar to what you get using the colon crafter depth predictions. And I guess this would also be nice in a clinical setting because you could get quantitative estimates of how well the colon was traversed, in a quantitative, like area-based sense, not just like qualitative, oh, we missed this area. No, this is like, you can measure the I guess the missed surface areas shows as black in this case. You could quantify that if you wanted to. Okay. Now just a couple of slides on what we're working on next, and what I've been interested in and where the lab is heading. So in recent months, I've been working more on like holistic 3D reconstruction approaches, creating interactive fly-throughs of colonoscopies. So this is using, I guess, relatively recent method called Gaussian splatting or neural rendering approaches. These are very short clips, so I'll play them a couple times. But these are fully virtual visualizations of the colon. So not just point cloud reconstructions, but we're also now trying to produce high fidelity renders of what is seen during a colonoscopy. And if a physician wanted to interact with these, there would be a file that they could essentially inspect from any angle that they wanted to see what was seen offline during the colonoscopy. Maybe do some like post hoc analysis. Precisely measure the size of certain lesions. Um, yeah, the possibilities, I guess, abound uh, in terms of clinical uses. But yeah, this is still a work in progress, and definitely something that needs more work and is actively being worked on in the field. We're also interested in reconstructions of, real anatomy. So I mentioned one of the limitations of using only silicone models. They're a step up from using like truly synthetic data, like the ones that we derived from CT scans. But definitely, it's a far shot still from truly or true clinical colonoscopy videos. So something that we're currently in the midst of doing is trying to reconstruct actually pig colons. So we went to this simulation facility near Boston to record some videos of colonoscopies that we did on this preserved pig colon, and then we're now trying to see if we can produce a physically accurate model of this colon just from the video, um, but also a work in progress. Our lab has also been interested in robotics. So we're in the process of acquiring now well, actually some silicone models which we can hook up to robotics to try to see if we can develop policies for automating and assisting in certain procedures, like resections and hemostatic management. And then finally, I am personally interested, and I've been talking to a lot of our collaborators at Beth Israel about this, is, using 3D reconstruction to improve clinical outcomes is one area that is, I think, of vital interest. There's a lot of conditions and diseases, abnormalities that are currently classified in a very imprecise sense. I've highlighted a few here. What you see on the left is hiatal hernias. So it's when the stomach, um, uh, a hernia is kind of a protrusion of an organ through an opening. So it's when the stomach herniates through the esophagus, and it's really quite painful. But the way that these are currently like stratified, for severity is pretty imprecise. There's a lot of like eyeballing by the physician. Again, a lot of like textual descriptions, not a lot of quantitative grounded evidence. And so this is an area where 3D methods, I think, have a potential to really improve things. The two on the right, the top right one shows Barrett's esophagus, which is a condition of the upper GI tract. So this would be actually moving again, maybe staying in endoscopy, but not colonoscopy specific. Um, where you could measure the surface area of Barrett's esophagus. It kind of appears as this like plaque-like um, lesion. Um, and you could use presumably 3D reconstruction to measure the surface area of these lesions, track them across time, and this would give you, very precise quantitative evidence for how far the condition has progressed. And the story for the bottom one, which is ulcerative colitis and IBD, is very similar. Right? There's currently a very rough grading system, like Mayo endoscopic scores, which I think there's been like literature recently saying that this is insufficient. It's not very precise. So how can we leverage computer vision to aid in disease quantification? So another clinical opportunity there. Yeah, I hope, yeah, I realize I talked for more than I was intending to. So yeah, thank you everyone for listening. Also, big thank you to Pranav, who's my PI, Tyler and Todd, who are my collaborators at Beth Israel, and Andrea, who's maybe in this call, who's a master's student at UNC, who's been working closely with me over the past 2 months now on 3D reconstruction. So, and yeah, and thanks to everyone else in the lab as well who's yeah, been invaluable. Um, oh, I realize I now missed some questions. Apologies. So, Anamika asks, when you conclude that colon crafter more accurately predicts depth in real clinical situations, are those clinical situations actual colonoscopy videos? That is a good question. So no, what we concluded is, so we're using the silicone models as a proxy for, oops, I went too far. These are the silicone models or examples of silicone models that we're evaluating on. Um, because clinical videos don't have ground truth depth annotations and it's virtually impossible to get them, this is kind of the best proxy that we can have for a quantitative evaluation. Beyond doing some sort of clinical trial setup, um, where we, apply a reconstruction for some clinical task and evaluate how it does in terms of improving clinical outcomes. Um, but yeah, the claim that we're making is weaker in the sense that, we're beating the baselines that we evaluated against on these silicone phantoms in terms of like temporally consistent depth estimation. So hopefully that makes sense. And then Abhishek asks, in the future, do you think this can be used in clinical settings, especially for the early detection of colon cancer or other GI diseases in some way? Yes, my answer is yes. I think we're still pretty far away from true clinical utility. But I think there's now a lot of interest in computer vision for colonoscopy and endoscopy in general. And the field is evolving very rapidly. Even, I'm not a veteran in the field since I started this work at the beginning of this year. Um, but even in these 9 months, I've seen a lot more papers come out about 3D reconstruction and about computer vision models for endoscopic procedures. So I'm really excited to see, I guess, where the field leads. I think, yeah, some of the later slides I've shown, I think, show some of the clinical opportunities related to like disease monitoring. Um, I think, yeah, I think in the near term, we can definitely use 3D reconstruction to help in surgery planning. I think the technology is already mature enough for that. When it comes to diagnostic tasks, I'm a little bit more skeptical, but who knows? AI always surprises me with the speed at which it advances. So um, TBD. Um, yeah.
I
Any
also
other
have
more
a
questions?
I have a question before
Yeah.
other people. So it looks like there's people who has questions, but I can go first. Either in evaluation or in training, have you guys thought about using paired when you're making these depth estimation maps? Have you guys thought about making paired uh, or making a ground truth depth estimation from a patient who has a paired CT plus colonoscopy? And I don't know how common for a patient to have uh, these scans available, but if you have both of them, is there a way where you can utilize the CT to get ground truth estimations for the colonoscopy video?
So yes, I remember initially when we started this, I had a lot of discussions with Pranav about doing something similar. The problem with that is there aren't a lot of patients who have these paired colonoscopies and CTs. And the the colon deforms. It's difficult to map the colon anatomy in the colonoscopy video to the colon anatomy in the CT, because the colon ends up moving a lot, based on the position of the patient. So if the patient is lying in a specific way when the CT is taken, um, and lying in a different way during the colonoscopy, or if the endoscope prods like a certain side of the colon, it'll deform in a certain way. So registering even the same organ, from a CT scan to a video is a non-trivial task. Um, and yeah, I think you would end up with inaccurate depth estimates, is my guess. At least I haven't seen anybody successfully do it. I hope that answers your question. Um, and I see two more questions. Anamika, go ahead.
Yeah, thanks so much, Roman. This is really interesting work, and obviously, you guys have put a lot of thought and time into it. I'm a surgical resident, and I think this is like very cool and very needed, this kind of workflow, especially because endoscopy is oftentimes one of the things that both in the inpatient and outpatient setting is really difficult to schedule. So
Mhm.
there's like everything's really backed up as is everything in healthcare. I'm wondering because I asked the question about the like real colonoscopy videos. To me, it just
Yeah.
seems like your simulation is great, and we do a lot of like simulation-based training in surgery. But when you actually get into the operating room, it's very different, right? And so,
Yeah.
like, I completely understand that you might not be able to get videos of colonoscopies, but it seems like this kind of model, if you want it to actually be clinically useful, should be trained on colonoscopy videos. So, like, how are you guys bridging that gap?
Yeah. So in a few different ways. So I think we're slowly now trying to move away from using silicone phantoms. And I think there's been more work recently on self-supervised learning for depth estimation without ground truth depth, leveraging large-scale like, unlabeled data. So this would be like an instance where we would, procure real videos of colonoscopies, and have a depth estimation model, maybe initialized from ColonCrafter or some other architecture, um, to learn depth. And in that case, it would be, I guess, clinically aligned, since it's been trained on real clinical videos. Um, and there are, at least in Boston, we have uh, a subset of videos which are like taken at Beth Israel, and in collaborating hospitals that we can access for this type of work. I think it's always tricky getting access to videos because there's a lot of questions and a lot of not red tape, but for good reason. There's a lot of restrictions around using that data because you want to make sure that it's de-identified and can't hurt the patients in any way. So yeah, in the long term, yes, I think we want to move towards real videos and not just train purely on synthetic data, um, and even silicone data. Um, I think what this shows is you can use synthetic data to learn like strong geometry or strong geometric priors about colon anatomy, which is already quite useful. So I can imagine a setting where you have maybe not a super large data set of videos, but you've trained at scale on your synthetic data, and you fine tune in some way on your real clinical videos to make it more clinically aligned.
Just a follow-up for that. So I know you mentioned your I guess like training on a it seems like a portion of a pig colon. Um
Yeah.
and obviously pig anatomy, we use it a lot as kind of an analog for human anatomy, but is there any barrier for you guys like getting a cadaver or like partnering with a med school that has a cadaver and training on an actual human colon? And if you just like, would you be able to accurately train if you train like multiple times on just one colon?
Um, Actually, that's something I haven't thought about.
Because I was at HMS for med school
Yeah,
and they have, I mean, obviously every med school has an anatomy lab, but there's multiple cadavers there. Like people are using them for different, obviously for studying and like research, but um, it could be something because obviously like a large portion of the colon is redundant, but so you theoretically have like lots of, I don't know, volume or surface area to train on.
yeah. Um, so because we already have access to some videos that were recorded from real patients at hospitals, so I'd never considered actually recording videos from cadavers. That's a really interesting use case. Does actually a follow-up question to you. Uh, how much does the like movement of the colon or how similar is a colon on a cadaver to that of a real person?
Oh,
Because I
not
assume
similar at
stuff
all.
like paracelsus.
Yeah, no, you're not going to be able to capture any of the motion. And I think your point is very well taken that the colon moves like so much, even if just from, standing up, sitting down, etc. So you're not going to be able to capture that. But I think like if you wanted to get the internal architecture of the colon, it's going to be kind of similar. It's just, it seems like there's the barrier. So I'm like obviously really invested in getting AI into hospitals, especially with regards to surgical use cases and but one of the barriers it seems like is just getting real data to train on. And so if it seems to me like maybe that would give you a little more information than the silicone model seems great, but like it's not a colon.
Yeah. Yeah, I think that's I mean that's exactly right. I think like both, purely virtual I guess digital synthetic data, can be acquired at large scales. That was one of the points of our paper. Uh, Very good for learning geometry. Silicone data is like a step up from that. Also very imperfect because you end up with these very idealized trajectories, and it's a lot more rigid. Um, yeah, yeah, it's something that I'll definitely think about it. I mean, yes, undoubtedly more useful than silicone models. I would agree with you. Um, and I think there was someone else that had their hand up, but I'm not sure who.
I just had a quick question
Oh
um,
yeah.
about the synthetic data. So if you got the 3D model from the CT,
Hmm.
correct? Um, so from what I know about colonoscopies, I think that they do inflate the colon to start the procedure, right? So do we account for that at any point in this 3D model of the actual air that's getting pumped in that would be changing, the radius of the, yeah.
Yeah, yeah. So the answer is no. In this case, so this is, I guess, a colon at rest. From the patient. I think most of these are in supine position, so they're laying down. Um, and I guess our focus is not necessarily on like how close these like I think the important part with this synthetic data set gathering is that it has the shape and the like the geometry of a colon. It does not model like the motion or the insufflation of the colon or any like truly realistic aspect of what happens in colonoscopy. Um, I think, yeah, I think it's a means for us to learn like to quickly learn colon geometry, is what I would think about it as. Because you get the folds, and you can see from these segmentations, you know, the uh, this data set construction gives you nice enough colon segmentations. They're imperfect. There's some artifacts here and there. It has the Hausdorff folds. Uh, it has the twists and turns. So if since we're training on videos, we can incorporate some somewhat complicated camera motions. But I think one of the conclusions of the paper that this is would be more for learning uh, priors more so than like true realistic colonoscopy trajectories.
Cool. And for the center line, for the virtual fly-throughs,
Mhm.
um, did you stick like strictly to the center line, or did you do some like offsets for it not being completely centered?
Yeah, we did a couple of offsets. I think mostly, trying to remember because this data set construction was a few months ago now. We definitely had augmentations for the clips. So we didn't just do like super smooth camera motions. I tried to incorporate slightly more complex camera trajectories where there would be like deviations of the camera angle and I think slight jitters of the position, although I'm not completely sure. Um, uh, yeah. Um, but nothing, yeah, nothing super complicated. I think that they're mostly just like very like smooth trajectories.
Cool. Sounds good. Thank you.
Yeah.
And sorry, one last thing. I don't mean to
Mhm.
belabor this.
No, no, go ahead.
For so for CT scans, we can order a 3D recon of the scan, right? That and the text, sorry, I don't know exactly how this is done, but they'll like recon it for you and then it should that's not how you got your model, right?
No, I actually did this manually, which is I suspect it ends up being a similar pipeline to what the text did. Since this is an open source data set, there wasn't associated like
Oh, I see.
segmentations.
Okay.
Um, but yeah, the I mean I use 3D Slicer and like all the segmentation and the centerline extraction is I guess software that's already included in the platform, which I assume is the same as what Tex would use. Um, Actually, my understanding is it used to be the case maybe that virtual like colonoscopies using CT scans were more common. Is that true? I think they used to actually screen for polyps, right? Using
Yeah.
CTs.
I
Yeah.
mean, I think the data is very unclear about all of this, and I'm not an expert on these by any means. I do know that in this country, in the United States, we consider a colonoscopy as the gold standard, but it is not the gold standard elsewhere. And that could
Mhm.
just be our patient population is different. There's a lot of talk about moving towards like Cologuard or, things like that,
Yeah.
which would help, I mean, like access. But at the same time, I don't know exactly. I'm not a colorectal surgeon, but I don't know exactly what their workflow is in terms of like using colonoscopy data to exactly determine like what portion of the colon they're going to resect or what the surgical plan is. I don't think it needs to be that granular though, because they typically will just like resect at a specific level that they know the cancer to be in.
I see.
So
Yeah.
when it comes to surgical planning, I mean, if you can use this to help somebody avoid getting like a colostomy or something, like that would be awesome, right? But I don't know
Yeah.
that I don't know like that the surgical technique the surgical technique I think like historically has accounted for what we can do, and what we can do is like we're not necessarily in a place where we can like exactly pull out like the portion of the colon and then reanastomosis. But then again, like people are doing different things everywhere. So sorry, that's like getting into the weeds, but yeah, this is a great talk. This is wonderful.
Yeah. No, thank you. That's really valuable insight. Yeah, the surgical planning bit I think came from my discussions with Tyler, um, who mentioned, and I might have misconstrued some of it or just played a bad game of telephone. Um, yeah, my understanding was that for just the communication about lesion locations um, was poor in some cases and needing more precise 3D information. But yeah, perhaps I made too bold of a claim that this would, completely solve surgery planning.
No, I think it's valid. It's also like most general surgeons are trained in endoscopy. And so I think like he might be alluding to if somebody's unclear as to like where the lesion actually is, maybe they just like do the scope themselves before they do the procedure. I know some attendings will do that. But again, like the workflows are it's such a spectrum.
Yeah, yeah, no, makes sense. Um, yeah, no, it's interesting that you mentioned the differences between the U.S. and the rest of the world. Um, yeah. Um, any other questions? Happy to take anything else.
I guess since there's no other questions, we can end here. Thank you so much, Roman, for the amazing talk. And thank you for staying with us more than the hour we reserved you for.
Yeah. Sorry for making the talk. I ended up being a lot longer than than I thought it would be. So thanks everyone
No
for
worries, no worries. I mean,
taking part of it.
it doesn't hurt and it benefits. So that's good. So this talk, as well as all of our future talks, are going to be uploaded on YouTube. Um, I shared the channel in the chat. Also, make sure to follow us on LinkedIn to stay up to date on our next talks and other events that we plan on doing. I'm going to share our LinkedIn in the chat. And yeah, see you all at another time. Bye.
Thank you.